right, so this is the first one, and I think everybody can see this. I'm just gonna go through it, and if you don't understand something, please ask now, or if you really don't want to, just see me after class. I wanna make sure we're clear about this. So they have 3 manufacturers, and a problem like this will appear in the file. It may be 4 manufacturers, there might be some other variations, but this kind of problem is typical. So the first thing is, you got 3 manufacturers, and they give the percentage of defective chips, 0.05 from A, 0.001 or 0.005 from A, 0.001 from B, 0.01 from C, and the proportion of the chips used are 50% A, 10% B, and 40% C. If a chip is randomly, or if a randomly selected chip is found to be bad, it's a probability from A. Now the way you always do this is first you have, this is Bayes' theorem, first you have to find the probability, basically a chip's gonna be bad if you randomly selected from any of them. Does everybody follow the thoughts on this? So down here, I've had a lot of odd things happen, but I can't even get it that way. All right, let's try this. So for this one, probability that a chip is bad really is probability of something being selected from A times the probability it's bad or defective, plus probability from B times the probability it is defective, plus the probability it comes from C times the probability it's defective. Does everybody follow me on this one? It's meant to be very straightforward. It's based on problems we did earlier on. So you get the probability that a chip is bad. Then after that, if you use Bayes' theorem, the probability that it is from A, given it is defective, you can say that times the probability it's defective is equal to the probability it's defective from A times the probability it is from A. And basically you're doing an inverse problem. And you do it the same time, the same way every time. And if you do it, those should be the percentages you get, or I should say the value you're gonna get. You multiply that by 100 if you want a percentage. You all with me on this class? Now, if there's anything that you see there that is inconsistent with the grade you got, if there's any answers that are correct on your paper but marked wrong, see me after class, okay? Just make a notation of that. Everybody with me on this? Do you recognize this problem from the, I think it's from the homework. I don't remember which homework. I literally took it. The only thing I did, I think on the homework, they didn't have defective chips, it was something else, but it was the same exact problem, basically. So the next one is a Gaussian. Now this is the one, if you know how to use your calculators, this should have been just a check. It should have been, the only thing I did is verify you know what you're doing with your calculators. If you wanted tables, I'd be happy to provide you with tables. So they give you the mean value of 2 and a variance of 3. A variance is sigma squared, not standard deviation. I think there might have been a problem with that, interpreting this. Do y'all follow me on this class? Variance is sigma squared. What's the probability of the voltage of being greater than 0? And again, this is a straight integration. You're really just integrating. If you have a density function, do you want me to write it on the board? Does everybody understand this? Does anybody want me to write it on the board? It's not meant to be hard. It was a straightforward 1 over the square root of 2 pi sigma, standard deviation, not variance, exp to the minus quantity, and it's going to be v minus the mean value, quantity squared over 2 sigma squared. It was meant to be straight. You put that in there. If you have your calculators, and some of you have the cumulative normal distribution, I think, some of you have other, others, you might say, forms of that, but then you integrate it from from the limits. In this case, from 0 to infinity, or take 1 minus the integral from minus infinity to 0, and you're going to get the same answer. What's the probability of the voltage? By the way, I think I put this, yeah, there it is. I put it in the math game. What is the probability of voltage being greater than 0 and less than 3? Now, you've already got the probability of being greater than 0, so the only thing you need to do is get the probability of being greater than 3 and subtract that off. Follow me, class, on this one? And you can do it, I mean, you can just rewrite the integral with different limits for, I think, Jagger has one where he can do that. Did anybody else have that in your calculator? You have, is it cumulative normal distribution? Which, is that the function?
Yes.
What calculator?
TI 83.
83? Which,
84 plus.
how many have 83 or 84 plus in it? Just 2 of you, 3 of you? Did you have any problems in any of that? Okay. I'm not gonna spend any time on it. What is the probability of the voltage being greater than 6? And again, check your answers on this one. I want to make sure everybody, because I think, you see how it's 0.01046. I want to make sure that there's no problem with a decimal point error or anything like that. Y'all got that one, right? Okay. If you need to see me after class about this. The next was the third central moment. Y'all remember this, central moments with Gaussians that are odd orders are always 0 if they're central moment. Y'all with me on this, class? Finally, the last part was just to make sure you knew what you were doing. What is the mean squared value of the voltage? Now, you could do the integration. You could take x squared times that density function, right, from minus infinity to infinity. But remember, it was 1 times 3, right? And this is going to be, the mean squared value is just the second one, so it's really just going to be, what, sigma squared plus the mean squared, right? So it's sigma squared, or the variance, plus the mean squared, and the mean was 2, so it's 3 plus 4 is 7. Meant to be just check a box, move on. These weren't meant to make you think for a long time about one problem. Finally, the last one is this communication problem. Now we actually outlined how to do these problems before. This is one I think people may have made mistakes with. And I'm not certain, but I'm just going to take 1 minute to make sure we don't make mistakes. And you might want to write this down. You will see a problem like this on the final. Please put that down. You will see a problem like this on the final exam, based on this idea. Now, it was not meant to be hard. That's the only thing I'm going to say. Now I need to talk about this, because this is something I think, I haven't looked at all the papers, but I think there was a problem. Anytime you have parallel connections like so, and you want, this is a sender and this is a receiver, and I'll just call this P1, and that's the probability that it's operating, correct? And this would be P2, probability of it operating correctly. You all with me? Now, if they're in parallel, you always go for the not operating correctly. Correct? Everybody with me? So you might say the not operating would be equal to 1 minus P1 here, and then not operating. 1 is going to be 1 minus P2 here. And we can extend this for an infinite number, but we're just going to do 2. You all with me? Therefore, the probability of it not operating, I'll just call it Pn, is going to be equal to this n1 times n2. That's saying it's not operating, correct? Because if either one doesn't work, it doesn't work. I'm sorry. If both of them don't work, then it doesn't work. But if either one works, it works. If 1 or 2 of them work, it works, right? So once you have that, that means the probability of this working or operating correctly is going to be 1 minus n1, n2, 1 minus in this, 1 minus p1, 1 minus p2. That should be clear. That's for parallel. With me? And we can extend that, and I will. If there was another one, if you just had another one here, like so, all in parallel, Then this would be 1 minus P3, and it would go on indefinitely for the number you have in parallel. And it's critical you see this, because this, usually when you get 3 or more, it starts to get somewhat confusing for people at times. Now, if they're in series, and it really doesn't matter how many links you have, but if this is P1 that's operating correctly, this is sender receiver, and it's going this way, P1, P2, and P3 here. Then the probability it's operating correctly, I call it P1, 3, operating correctly is just P1, P2, P3. I'm just saying the obvious now, and I don't mean to, I'm not trying to rub salt in your wounds if you made a mistake here, but I've got to make sure you're not going to do this again, especially if you're here. Now, in these, if you just look at this and assume that we know the probability of each one of those working, y'all with me, class? Then what I would do, forget about the question on this one, we'll get to that in a second. Every time you see a series link there, replace it by one connection. So CD you'd replace by 1. If you just want to take a look at this, the overall probability that from sender to receiver it's working right, this would be PC times PD with 1 link. Then from here to here, it would be PE, P times PF. Y'all with me? Now you have 3 links in parallel. Then you would do you would start by saying it's 1 minus PCD, that this is not operating. This is going to be 1 minus PB. And this here is just going to be 1 minus PE, PF. Y'all with me, class? Multiply those together, and then take 1 minus that. That's the probability of this working. Y'all with me? Just that little unit right there, the diamond. Replace that whole thing with just that 1 link of it working. Whatever the value is, it doesn't matter. Then multiply that by P. I think people may have forgot to multiply it by that A link. I don't know that for a fact. I'm guessing is the kind of mistakes that might happen. And then you would get P of A times that probability, that whole long mess. For the second one, then you get the probability of it working. Got me? Now what I tried to do is start with a more basic problem right here. Determine the probability of the communication link working if F is not working. Now this one was just meant to just make sure you understand the basics. If that's not working, can you see how this whole link gets taken out? If F is not working, how many can see that? Are you good with that or not? If F is not working, it's not there, this is a dangler, it's not doing anything, right? C is a dangler. Can you all see that?
The question is though that if F is working.
Oh, I'm sorry. I'll get to that in a second,
Okay.
but I first wanted to do that because I think some people make a mistake that even though isn't there one with this?
Yeah, the next 2 are not working.
All right, yeah, and I think people made mistakes with that one because if any of these series links isn't working, the series link ain't working. That's the whole idea. They just remove it. So this one says the probability of F is working. Well, if F is working, then that lower link becomes probability of E alone down there that it's working. You all see this, class? Because we're guaranteeing this is working, and 1 minus the probability of E would be the probability of the lower link not working. Now, I want to say this. When you look at this intuitively, just look at it. If this is guaranteed to work, then the probability that from sender to receiver will be higher than if this is probabilistic. Does that make sense then? If we know F's working, we're going to get a higher probability of sender to receiver than we would if we don't know F is working. It's still probabilistic. Y'all with me? And if you remove F, if F isn't working, then it's going to be lower still. What I'm trying to get at is how this thing should manifest itself at the final result. So the next part is determine the probability of the communication link working if C is not working. This is the one I should have mentioned first. C is not working, doesn't matter about D. You all see this, class? This whole top link's taken out. All right, if C is not working, then it's just the probability of B there, or 1 minus the probability of B of the middle link working, right? And then it'd be 1 minus the probability of PE, PF at the lower link not working. So the probability of the link not working is really that. The two multiplied together, and 1 minus whatever the result is would be the probability of the link working. You can replace that with a single link times PA. PA is always going to be there. Y'all agree with this class? Finally, what's the next part? Determine the probability of communication link working if C and D are not working. Isn't that identical to the prior one? Can you all see that right there, class? If C and D are not working, it doesn't matter. If C is not working, it's the same thing as C and D not working because they're in series. Y'all follow me? Finally, what is determine the probability of the communication link working? And that should have been clear with me. Now I'll show you one that will get you that I would expect on the final exam. Since you were here, you'll get it. Maybe other people. This one I want you to be clear. I'm going to put it here and I'm going to take my time. But this is the one that I'd ask about. You should have an idea how to do it. I'm going to ask the class. I did not cover this one in detail. I mentioned it, but I didn't cover it. So we're going to have, and all these things are going to be the probability of each link working. From here to here, I'll call this PA, right? And from here to here, PB, I'll give you time to write it down. From here to here, hey, can you turn on the lights for a second? Just hit all of them. PC, right? Then, just hit all four corners, yeah. PC right here. Then we're going to have PD, and then PE. But I'm going to do this. Actually, draw this a little bit better so you can see it. And this is going to be PD, PE, and PF. You'll notice that F can be bidirectional. In other words, information can flow either way. Y'all with me, class? Write this down. Then I'll come over here, and this is just going to be a dead link. It's going to go right here to the receiver. This is a great problem. So what I want to do is ask the class now, take a moment and ask yourselves this. What is the probability of this working? This communication link. How would you do that? Ask yourself this. I want to make sure we're clear. Anybody have an idea? How would you do it, CJ?
Find every path the information could go in series and then multiply.
Okay, show me what's in series.
So PB, PC, then PB, PE, or P.
These are not in series. This one breaks off, right?
So we can't
It goes here. What is this called? If I thought of a circuit's term for this. There's a well-known term. What do you call that? It's a delta Y connection. How many remember that? All right, now we're not going to do the transforms. Trust me, I'm not asking. There is a transform for that. Don't worry about it. But here's how you would do it, and I think you would, if you were given time, you would think this through. So let's first ask ourselves how to do it. Well, if I looked at this, it would be the probability of that occurring first. You all see this? Now remember, I'm saying PE not working, right? So if you look at this, can you all see how to do this one? If this is there, it would be what? It would be the probability of this times this would be the probability of that working, right? And the probability of this times this would be the probability of the second one working, right? And then if I took 1 minus quantity, 1 minus PBC times 1 minus PBE, I would have the probability of that working, right? multiplied by PA, I would have the probability of this system working. Do we agree with that? Let me just show you this, and I'll put this down. So for this system, I'll call this A. The probability that this works is going to be really P of A. It has to be that. And then it's going to be 1 minus, and I'll call it PB, right here, PC, times 1 minus PD times P of E. And that would be the probability of this first setup working, this configuration. You with me? Y'all see it? Now look carefully at this. Now, take a look at that. Then, take a look at this. Let's assume this is for the middle leg, PF not working. Now, if this is working, y'all with me on this? Watch your notes. If it is working, can you see I've got 2 in parallel here? I want you to see this. You agree? I got 2 in parallel there, right? And then once I reduce it, I have 2 in series. Can you all see this? With me? Now, I'll call this PA bar or something. PA bar. So this is where the middle leg is working. So what would that be? Well, you know, call it PA bar. It's going to be, well, it's always going to have the PA there, right? No matter what I do, that stays. Can you all see that? With me? I want to slow down. Can you see in the back? See, Judy, you can't see it? All right, now what do I write here? Well, these 2 are in parallel, right? But I need to take 1 minus PB here and 1 minus PD here, right? And then I need to take what? 1 minus PB times 1 minus PD, and that's the probability of these 2 replaced with a single link right there. Can everybody follow me on this, class? I want to make sure, and I don't want to go too fast. Then I have to multiply that by 1. Now remember, this reduces, and this is series, so then I have to multiply it by, and I'll stop for a second once I do this, 1 minus the quantity 1 minus PC, right? Times 1 minus PE. And that would be the probability for this configuration as shown. You agree with that? I'm running out of room. I'm going to do it over here. Can you all see the final probability? If you just take a look, we've got 2 different situations, right? So if we want the probability of this working, first we start with the probability. I'll write it down here. The probability of the system working. Take the probability of the first, and I'll just call that P of A, right? And what's the probability of that happening? Well, it would be that times 1 minus the probability of the middle link, and I mislabeled it there, but it's actually P of F, right? 1 minus the probability of F, because we're assuming that the middle link in this one is not working. Do y'all remember this, class? Do y'all see the rationale? Plus what? P of A bar, right? Now we take a look if it's working times the probability of it's working. And that would be, in other words, we know the probability of the middle leg either of working, right? So first I'm going to say the middle leg isn't working for this P, the last leg right here, the vertical linker, not working. Now I got to find the probability if the system works for that one. So find the probability of A, which I'm calling, then times 1 minus the probability, because that's the probability of it not working, right? Plus the probability of A bar, or the probability this thing is working, times the probability of the middle link, P of F working. Can you see the rationale on this? Let me see your hands if you can. Now that kind of problem on the final exam is guaranteed. You can write it down. If it's not there, sue me. But I promise you it'll be there in some form. I don't try to get too tricky with this kind of a problem, but I'm just going to tell you, now think about this. I could make it really scary and do one thing. I could then do this, right? Something like that. What would be the difference? Well, go ahead. First, you start, just let me put it this way. Start here. Just that, can't I replace this whole thing, or I should forget about A, but replace this whole thing with one link with that probability of working. Can you all see that? Let me see your hands if you see it. Can you see it? Can replace this whole thing with that over there. One link of it working, right? Subtract A from it. I'm not trying to get, and then what? Here's another link. They're in parallel. You all should be able to rationally figure this out logically if you understand the concepts. Y'all with me, class? And here's the danger. Somebody's going to try to write one equation with everything there in one compact equation, and usually it doesn't work well. Start by breaking it down into basic parts, either working or not working, times the probability it's working or not working, and keep reducing it that way. I'm always concerned about this problem because I know the kind of trouble kids can get into when they're tired. They get real confused easily. And final exams are not the place for people to feel refreshed usually. All with me, class? Any questions about that problem? I thought this is a great problem, by the way. Okay? Elijah, did you have a question or not? Anybody? The logic on this should be clear. But I know from past experience it can be confusing. All right, now hold on. Yeah, let me get this first, make sure it's working. Okay. Go ahead. I'm not trying to waste your time on that one, but that's a problem I thought about putting on, and then I thought, no, that would be a little much. We haven't really gone through that in the detail. We did do you remember that problem being put on earlier in the day? Like, how many weeks ago, but we put it up there when we were going through chapter 2, remember? But that problem itself, I think it was 2, is, see in the book, in Stanley Chan's book, he has a problem like this, but it's only 2 links. It's not, you know, he has a sender-receiver kind of thing, and he has 2 sources, a 0 and a 1. He does not have the complexity that I'm showing you there. Okay, enough said about that. Okay, for this one, now grant you, you didn't have a lot of practice with these 2, where we have 2 random variables and a joint distribution, but there was one overlying factor that the integration of these, of that density function over the entire range of possible values has to be 1. That's the one thing I wanted to make sure. Y'all with me, class? So the only thing you really had to do is integrate this, a e to the minus 4x plus 3y, and just from 0 to infinity from x and y. And it has to be equal to 1. Do you all agree with that? So a is just equal to 1 over 4 times 3, or 1 over 12. I mean, sorry. That would be, the integral would equal, a would be 1 over that root 12. Do you all follow me, class? Everybody understand this one here? I didn't check how many people got it right or wrong. I just asked. Was there any problem with that? You just do a direct integration. Now, once you have a, the probability of x really less than a half and y less than a fourth. Now that's just a double integral, right? You got the joint density function. Now you integrate over those ranges. Can everybody follow me on this class? Is there any problem interpreting that function? Only thing I can think of with this one is making a careless mistake with the integration. That's the only thing I can think of, and that can happen. Sometimes what I see is that minus sign right there is not brought into the integration. Somehow it's just dropped. But overall, it should have been straightforward. And finally, the expected value of these 2. Well, the expected value, if you multiply these times x times y times this, That's an integration by parts, but technically you only have to do it one time, because both of those, by the way, did your calculators, I think I told you that you need to be able to do that kind of a problem, didn't I, before? Did you have any trouble with your calculators doing it? I figured it was easy to do on a calculator. Integration by parts, you would have like x e to the minus ax dx, then you would have to do a u, which would be x, and then a dv, which would be e to the minus ax dx, and then you would have to do the integration by parts and get uv minus, go v du, and you can do it that way, and it comes out nicely, but you only have to do it once, because the form of the integration is the same for either x or y in this case. So if you did that, this one should have been straightforward. You could do this one with your calculators by setting up the integral rate, or I think I did that right here, or you could do it by integration by parts. In either case, it shouldn't have been difficult. Were there any questions about this one? Do you remember this problem, by the way? It wasn't 4 and 3. What was it? It was 2 and 3, I think.
2 and 3.
What's that?
It was 2 and 3, yeah.
What was it?
2 and 3.
2 and 3. That's what I thought it was, because I literally ripped it from the home. All right. Matter of fact, all these problems came from the home. Finally, this is one I emailed you. Do you all remember this problem? It's identical. Not a changed thing. It was just to make sure. You remember this? This is going to be permutations and combinations. That was the whole idea on this one. And we had this, I think, in the first 2 weeks, if I'm not mistaken, didn't we? Permutation and combination is the only thing if order's important or order's not important. So this one, you can look at what I emailed you to find out it's identical. It's basically identical. And even the numbers, every number, there's not a change in this. So what is this one now? It's 4 balls is infidel, 3 of them are low, it's 6 in cabaret Sauvignon, and she wants to serve 2 bottles as infidel. Serving orders and how many different ways are there. So this is that permutation combination thing right here. C is combination, P is permutation. Because there's only 4 bottles. The first one, you got 4 bottles, right, as infidel. How many different ways? Unique ways. This would be a permutation to serve 2 at a time, and there's going to be 12. Does everybody follow me on this class? And I think I had the permutation. Didn't I have that down? No. So that's an n factorial over k minus n factorial, right? That one. Finally, B, you can go through this. If 6 bottles of wine are to be randomly selected from 15, how many different ways of whether we do this? You'll notice order not important, so combinations for that. And you can look at the formulas. They're basically, this is the problem we outlined and did in class. I think we did this one, but I don't remember exactly. We did it in class, yeah. Finally, 6 bottles are random selected. How many ways are there to take 2 bottles of each variety? Again, order is not important, so it's going to be the lower value. If you had permutations, if order was important, you have a much higher value. 2 bottles of each variety being chosen. Finally, the last one, 4 bottles of random selected. What's the probability of all of them from the same winery, and that's the last part right here. And that's extremely small. Were there any questions about this one? Because it wasn't meant to be a difficult problem. You did have to understand combinations and permutations, right? Now, the final exam, there's a logical question is would we be expected to understand how to do a problem like that? Yes. The form of the problem may not be with lines. It may be chip vendors or something like this, 4 chip vendors, 3 chip vendors with a certain probability. Can y'all follow me on what I'm trying to tell you? This type of problem is fair game. And if just make sure you understand permutations versus combinations. And remember, for that one, if there's probability involved, then you need the binomial distribution. Do y'all remember that? Binomial distribution would be n factorial, n would be the total number, over k factorial, that would be the number that met that you're actually selecting, over n minus k factorial. That's out in front, and that's take a look at that, that's the actual, permutations, then it would be times the probability of a successful event to the k times 1 minus the probability of a successful event to the n minus k. If there's a probability of, you know, an event occurring or not occurring, it have to be binary. I'll give you more problems related to that so it won't scare you. And of the problems on the test that I thought were the hardest, this is the one that was, in my opinion, the most difficult or challenging, but I don't know how, I didn't take any score in that. All right, any questions about this? I'm gonna try to be fair with you all the time. What my goal is now, I'm gonna go to some slides only to present the theory and the formulas, and then I'd like to work problems. The more problems I think we work, in my opinion, that's where you see how you apply the ideas, the formulas, theorems and axioms and all that. Because this stuff can, frankly, overwhelm you if you're not careful. For life, man, I don't know why it locks up like this, but it does. I gotta do this all over. I think I have the slides of this. Can everybody get to these slides right here? Except me. I don't know why this thing's so slow. Anybody having trouble with the internet now? Anybody using the internet? Guess there's something going on. This thing's really slow. It's not working at all. We did all these problems early, and they were trivial problems. So now this conditional probability thing, remember with Bayes' theorem, it came down to this. If you wanted f of x given y, you need to find just the density function for f of y. You divide it into x, f of xy, and vice versa. Let me ask you one thing before I continue. And I'm trying to just do this to make sure everybody kind of remind you of this. If I look at this density function right here, x plus y from 0 to 1, both values, there was something called independence or non-independent. Are they independent or dependent? Is one dependent on the other, or are they independent? Remember? If you could go ahead.
I know they're additive, that's significant instead of multiplying together.
These are not independent because they're additive. You can't factor out just an f of x times just an f of y. Y'all with me? If it was multiplied, it was x times y, then they would be. Y'all with me on this question? That's important. Remember that. So for this particular problem, you have to go and get f of y by itself by integrating out f of x, and then divide that into f of x, y. But there, when they give f of x given y, now you have to plug in the value for y, the actual value here. For this particular problem, it's worth just mentioning, if you haven't gone through this one, I'm gonna just briefly do it. So they want, given that joint distribution, probability of x being greater than half, given that y is 1/4. Now this is the typical base there, so we're gonna get this density function first. What it means is we just take f of xy and then we divide it by f of y. Now, if you look at this, and we wanted f of y, we have to integrate x plus y dx from 0 to 1. Y'all follow me on this, class? This will give us the f of y. I'll be doing problems where we do this on the board in a bit. Once we do that, he shows you f of y right here. It's 1/2 plus y. You'll notice y has no given stated value. That is just f of y. And you'll notice when, if you take a look at this, that density function right there. This is what I want to see. Well, if y equals 1, this particular value is what? 3/2. It's greater than 1. Can you all see that? That automatically tells you that if you ever see something like that, it means these are not independent. They're dependent on one another for this thing to work. So the probability of x given any value of y, and that's what that line means. You start with f of x, y, you divide it by f of y. But y here is said to be 1/4. So now you take 1/2 plus y and you put in 1/4 here. And that means you get 3/4 as what you're dividing by. And then the probability that x is greater than half, now we do have the right density function. F of x plus y is on top, but here y is 1/4. It's important that you see now we put in the actual value for y there. Y is 1/4, and f of y here is just evaluated as a constant. Y equals 1/4 or 3/4. Then do the integration, you get 2/3. I'm going to caution you about one thing. You should have access to these slides on OneNote. Has everybody seen these there? If you make sure you look at this carefully, you can do this and understand the ideas behind it. Because this can get hairy. Here's what I see. I want you to listen to that. That's the correct way to do it, getting f of y. And then getting f of x given y from this formula. Here's what happens. Right here, they'll put in y equals whatever the value, 1/4. Y'all with me? And then they'll simply integrate that right there, and they'll get the wrong answer. Can everybody see that? They won't correctly get f of y first. You just integrate that for the range from 0 to whatever it is, or from 1/2 to 1, you're going to get the wrong answer. This is the correct method for doing it. You have to use base there. Do you understand what I'm trying to tell you, people? That is a typical mistake, characteristic mistake. Y'all with me? So make sure you first get f of y, and then f of x given y before you get the probability, because you have to have that. If it says find the probability of x being greater than given y is this, you first have to get f of y and divide that into f of x comma y, then replace the value of y by the given. Finally do the integration on x to get the correct answer. All right. Said that. We'll do 3-2-2. Did anybody do 3-2-2? Let's sign that one other time, I believe. Did anybody do that? No? If you don't mind, we'll do it. And I'm going to shut this down. there's a few problems I want to get to, and remember, give me 1 second. Now, chapter 3, I'll try to really, really make it clear what stuff is important and what I think is difficult for you to grasp the type of problems, and at least try to spend, like, if you can, every day or at least every other day, some quality time on this, so it sticks with you. All right. So this is 3-2.2, I believe it is. And it refers to an earlier problem, doesn't it?
It does, it says this for the joint probability density function, and that's gonna be fxy equals kxy, 0xy, so equal to that.
X comma 1, less than 1?
Yes.
All right, they're referring to this density function. Before I go any further, if you have that, this is similar to the problem you had in the exam, right? If you look at this, how do I get K for this one? In your own words.
So integrate inside equal to 1.
We know if we take f of xy here, dx dy, over the range of values, and I'll put omega, whatever the total, you might say xy extent is, right? This one's a nice one. So it's equal to k, and I can take that out in front. I got two integrals from 0 to 1, 0 to 1, of x, y, dx, dy. I'm just stating the obvious for only one reason, to make sure there's no steps left out where a person could have a question. With me? When you do this, k comes out in front. By the way, this has to be equal to 1. Let's say that. If you do this, you get k, right? Now if I integrate x dx, I get x squared over 2. Evaluated from 0 to 1 is just 1/2. And then I get y dy integrated, or y squared over 2, from 0 to 1 at 1/2 again, equal to 1, and that means k is equal to 4. Everybody with me on that one? Meant to be clear, simple. I got that. So now we know we're talking about a distribution. This is pretty routine right here. So the distribution function is actually 4, right? And it's 0 else. So now, what's the question?
Find the conditional probability density function f of x over y.
Given y. That means the slash means y is going to be stated explicitly as a value. Now, if you remember, what I've shown is, that is f of x, we can do it with base there, over what? Fy of y. Isn't that correct, class? By the way, I think I put the solutions for chapter 3 up, didn't I? You remember? For one, can anybody confirm that besides CJ?
They're in the solutions manual.
I put up, yeah, I mean, but chapter 3 is shown entirely. There isn't like a gap with a problem or two, I believe.
It should.
What?
It should.
All right. So anyway, do you all agree that would be right? And we could do, I put it this way, but we could also do it. We could take f of xy times f of y equals f of yx times f of x. Do y'all follow me? We could do it that way too, but we're doing it this way because we have that value. So how do we get f of y? Fy of y. I'm just I want everybody to just form that question at least, because I'm trying to make it real. Now, I'm just curious, how many know how to get it? I'm not going to call on you to tell me how many know how to get it. All right, now, anybody want to volunteer?
Just take the integral of it with respect to x.
Integral of what?
The xy.
F of x comma y from 0 to 1, right, of,
dx.
y'all follow me? making it clear, so what do I do? Let it go from 0 to 1 of 4 x, y, dx is gonna be 1. Well, that's 4 comes out in front, integrate x dx, x squared over 2 from 0 to 1 is a half. It's times y. I thought I did this one, so it's 2y. And this is gonna be y greater than 0, less than 1. Correct, class? So now I come down here, and I say I have 4xy divided by 2y. And you'll notice one thing that's obvious. It's not gonna be a function of y. You all follow me on this? So you get 2x, and this is for x greater than 0, less than 1. That means whenever I put it just that down, every other place it's 0. That's what I'm implying without saying it. Just bear with me on this one. There's one really obvious thing about this. Remember, if they're independent, f of x comma y is equal to just f of x times f of y of y. Can you all see that? Now, I mean, is it? Just take a look. This is 4xy. Well, f of x is 2x. I mean, sorry, x is 2x, f of y is 2y. Can you see how they're separable? What I mean by that is one value. Y can have any value at all. It does not affect f of x at all. And if that's the case, then if I want the probability of x, what is the question again?
It's just to find the conditional probability density function.
That's it. In other words, there's no condition on this one. They're independent. Y'all with me on this, class? It doesn't matter what y is. That is what the f of x is. And if I want the probability of x being between any values, just integrate f of x. That's it. That's my point. What's the next part? If there is one.
Find the conditional probability density function f of y given x.
Okay. Y'all agree with that? We got f of x and f of y. And if you multiply them together, you get f of x comma y, the joint density function. They are independent. What's the next one?
That's the last part.
Okay. Now, what's the next problem? And that's 3-2.3. I'm just curious.
It says a DC signal having a uniform distribution over the range from -5 to +5 volts is measured in the presence of an independent noise voltage having a Gaussian distribution with 0 median variance of 2b squared. So it just wants you to find the conditional probability density function of the signal given the value of the measurement.
All right, this one would involve getting the probability density function for signal plus noise. And I'm going to just mention this. And he's going to have the conditional probability because he's going to say of signal being greater than or less than a certain value, isn't it? Or is the signal plus noise being greater than or less?
Well, the next two questions is find the best estimate of the signal voltage if the measurement is 6 volts.
Okay, what they're really talking about, the maximum value of, basically, given 6 volts is measured. Remember, that's the sum of noise plus signal. What is the best estimate of the signal? What you have to do is get the density function of signal plus noise. Really what you want is the density function of signal given noise. All right, so that means what you're going to do is get a joint density function of signal plus noise, and you have to divide that by the actual value of, that would be the noise function, but this is going to be a little more than I'm going to get into right now. I don't think I have time to do this one in its entirety. What I'm going to do though is show you one other thing, and this is important. I'll get to those problems. I wanted to show you this one thing. Let me see this book for a second. I well, I'll tell you where this is, because you have a copy of this chapter. That's a big problem, by the way, what you just said. But it wasn't assigned yet for a reason. This is a little confusing part. All right, we have the probability function of a signal, by the way. You can get the other one fairly fast. All right, this is in section 3.4, and it's really going to be the correlation coefficient. This is, I want to start this today, and I will I'll do my best to make sure you see this. In the slides, he has a really nice slide presentation of this, but if you have two variables, and I'm just going to say this before I say any more. If, say, this is x, a random variable x, and this is a random variable y, okay? Now, if you look at this, and you see something like where if you just measured values, there's no pattern. You know with me? It means they're uncorrelated. Now, I'll get to this in a second, but really what it says is there's something called a correlation coefficient. And the symbol is rho. And I'll explain this. And that's equal to the expected value of random variable x times random variable y minus x bar, y bar over sigma x, sigma y. And there's probably a different way to write this, but yeah, this is shown on 133. I'll tell you where it comes from. Getting back to this is called the correlation coefficient. Usually they put an x, y here because you want to see what they're talking about. Now I'm going to tell you what it means in plain English. See how nothing here is, there's no pattern. It's just all over the place. One thing, if I know the value of x, I can't tell you the value of y or anything like that. Now, I'm getting to a point here. Any slides do a great job of this. But if I see this, where for every value of x, there's a value of y that is predictable. Or it's, what do you call that? It's a straight line. If I know the value of one, I know the value of the other. Y'all with me? Correlation coefficient for that case would be 1. We'll prove this. Y'all with me, class? If I saw something like, now remember, this has to do with this value, the correlation coefficient. So the straighter the line, you might say, the more, or the closer the value is to an absolute 1. But this would be a positive correlation value. There's also a negative correlation value. They're still related, closely related. It's just that one is inversely proportional to the other. Can you all see this? Now I'll get more involved with the slope of the line, because you can obviously say, well, what if it's just straight like this? The value of x has nothing to do with the value of y. Can you all see this? But at least, if you look at this, the value of y has only one value. That means, in a sense, you only have one statistically varying value. Can you all follow me? There's more to this, but I'm trying to give you an idea what this correlation coefficient actually means. So, how did this come about? And here's what they do. This is called covariance. Have you ever heard of covariance? In the book, you're gonna find out later, when you get into your senior level courses and stuff, when you get communications, there's a lot to do with covariance and, or correlation. And there's all sorts of definitions, I'm sure, that aren't included here, but this is the covariance covariance matrix. And what they do is this. They take the expected value of, if we have two random variables, x minus x bar, so they're getting rid completely of the mean value, times y minus y bar here. Sometimes they normalize this with respect to the standard deviations. I want to just take a look if he does here now. He's not doing it for this one, but he will for the actual correlation coefficient. If you take a look at this, this is going to be the expected value of x, y. Now you can see this, x times x, right? And then, if you look at this, when I take x bar times y, or x times y bar, and you get the expected value, just take a look at this. This is going to be minus the expected value of x, y bar, minus the expected value of y, x bar. Here what I'm doing is multiply the first xy, then I multiply these x bar, y, the outer ones is going to be x, y bar, right here. And finally you're going to have plus the expected value of x bar, y bar. Can you all see? I'm just expanding this right here. I want to take a moment. You all with me, class? Just let me finish this stuff. When you look at this, this is, we don't know this yet, because we don't know if they're uncorrelated or not. X, Y. Now, minus. Can you all see that y bar is a constant, right? Take it out front. What's the expected value of x? X bar. You all with me? So this is x, y bar, and that is x, y bar, and that is x, y bar. So I have x, y bar minus 2 x bar, y bar, or simply minus x bar, y bar is equal to what this is. This is the covariance. I might as well. And now if you take the covariance right there and you divide this by sigma x, sigma y, now you get rho x, y, and that's the correlation coefficient. We're going to talk about how to calculate this and some of the tricks to calculating this, you might say, for a lot of different cases. I wanted to start this today, and I'd like you to look at exercise 1.35 and exercise 3-4.1 and exercise 3-4.2. And this is on page 135 of the posted book. I'll put that up there. But the reason I'm starting this, I'll get to these other conditional probability. This correlation coefficient simplifies a whole lot of stuff. Once we get this, and you'll see that it'll become much, I shouldn't say much, in my opinion, it'll become simpler to get the right answer for a lot of these joint density functions of anything you want. And I'll have to get into that next time. All right. We don't have class Friday, so drive safely, but we do have class Monday. I don't like to give homework over break. I want these two things, and I'll ask you to do maybe one other thing, just to, break, I don't wanna spend too much time cramming a lot of this material in the last, we've got 4 weeks left, roughly, I think. What I wanna do is get a head start. We're gonna get through parts of chapter 4, and then we get into something that has a lot to do with communication. They're called spectral energy density, spectral power density. But those are more complicated. Now, the